There it is.
Okay, are we we're
Yep, we're
recording?
live. Hi, folks.
Okay.
Welcome to the February 2022 Northwest C++ Users Group meeting. The only announcement I've got tonight is I just wanted to note Microsoft, if you might have read, has opened up their campus or is starting to open up their campus. At least for the time being, I think we'll probably continue to meet remotely. The idea of getting 15 to 30 of us in a room for an hour and a half still isn't sounding like a great idea. If people have strong feelings a different way, let me know, and we'll kind of watch things as they unfold again. Any case, with that, tonight we have Daniel Hanson from University of Washington, and I'm going to turn it over to him. Thank you.
Okay. Well, good evening, everybody. I'm going to present here on some things that I've learned about C++20. I have been trying to write a book on modern C++ for finance. Shameless plug, the first 2 chapters will be coming out in early release fairly soon. But as part of the process, I've been researching features in C++20. And so it's really motivated me to learn. So I thought I'd share a few things that I've come across. And so I guess we'll get on with it. Okay, so the topics I'm going to cover tonight, first we'll talk about modules, and then a new feature which is convenient for those of us who do computational programming is the mathematical constants library. Then we'll move on to the spaceship operator, ranges and views, and then conclude with the date library, which is slated for C++20. More about that when we get to it. A couple of remarks. There's also a new edition called Stood Format, and I had originally planned to actually cover this, but I just, it is a bit much and didn't really have time for it. But you can see it in the sample code that will be posted on the NWCPP website when we're done. It's a convenient little tool. It allows you to display messages to the screen like you would, say, with C#. So it's a convenient feature if you're, for testing and that sort of thing. And then also their concepts. I'd also thought about bringing this in, but with everything else, there just wasn't enough time. And in fact, I'd probably need at least half the time to talk about concepts. And ideally, we would need actually a full session for this. But with that, just moving on here, just a few disclaimers and caveats. I just so you know, this is a high-level introduction, and I'm just sharing what I know and what I've learned about C++20. So I hope you're not expecting a deep dive into some of the details about these things. This is more high level and from the perspective of someone who uses C++ and modern C++ to solve problems. And I will fully admit that there is still plenty that I need to learn. So starting off here, we'll look at modules. And I've got to say, I love modules. They're great. Why? Well, we can say goodbye to header files and include guards. The other thing is that imported modules will not leak to other modules. So if, well, we'll get to that in a moment, but unlike hash includes, if you include them in one file and then include that in another file, then everything comes along with it. It's not the case with modules. One more thing that's nice is if you want to, you can write implementations inside declarations without guilt. And a very nice consequence of having modules is you can write function implementations where you now just have exported functions that are visible to the public, and then you can have like a class, and I put it in quotes, what are essentially the same thing as private variables that are private to their they're global among functions in the module, but they're private to the outside world, just like a private variable on a class. And similar to private member functions on a class, you can have non-exported helper functions. So in the past, if you say you wanted to write something as a non-member function, but it depended on, say, several helper functions, that would all be out there in the open. Now you can actually hide those implementation details. And one more thing that's nice about them is you can get faster compile times, and this is actually a consequence of this point here. Again, explaining this would be it's above my pay grade, so I won't get into all the hows and whys. But the upshot is because we don't have this problem anymore, and you don't have all the included files coming along and so forth. That's one of the reasons you can have faster compile times. Okay, so just as an example of writing a function in a module where it depends upon helper functions, I'm just going to use a simple example here of a function of two real numbers. And so there's one public facing function. So this is the exported function. And what it will do is set function parameters A, B, and C, and then the two variables it will take in X and Y, which are used to compute the result. What it's going to do is it's going to take the results of these two non-exported functions and sum them up and return the value. Again, it's a very simple example, but it illustrates what you can do. Our two helper functions are very simple. One is a linear function of x, the other one's a quadratic function in y. Again, these are not accessible outside the module. It's only the exported public function that the outside world can see and use, and it's just going to take the results, sum them up, and return the result. Then there are the internal variables. Again, you can think of them as encapsulated like on a class, and these will be the function parameters and the two function variables. So again, these are accessible to all the functions within the module, but not outside. Okay, so the way that you create a module is you define it by putting the line export module and then the module name followed by a semicolon. This allows you then to import the module in other modules and source files. We'll declare the module variables that you see here. So these first two will just be the results of the function of x and function of y, and then the three parameters. So in this case, we'll declare them and then have separate implementations. So here they are. Again, this is just very simple. So linear function x, quadratic, and y. There is no export keyword here. So that means that these are internal to the module only. The one function that is available is the one that is exported, and that's done by, again, putting the export keyword in front of the function signature that you see here. So it's like a class, it's going to set the parameters and then just call each of these functions, take the results, sum them up, and return them. So again, the key thing here is in order for the function to be usable outside, we have to put export in front, and then what it's going to do is just call the helper functions inside. One thing to note about using headers is there's a proposal to reorganize the standard library into a standard module version. And this is the reference. It was written by Bjarne Strustrup himself. This was hoped for in C++20, but it looks like it will now be pushed to C++23. It's when it will be available. There is a draft version that you can get with the Visual Studio compiler. So it's not standard, but it gives you an idea of what is probably coming down the road. In the interim, though, what appears to be standard are these things called header units. And these apply to almost all of the C++ standard library declaration files. And so, for example, instead of hash including vector, you can treat it as if it were a module by putting import and then vector as usual, and then followed by a semicolon. And as I said, this applies to almost every header unit or every declaration in the standard library, except for those that are inherited from C. So for example, C assert, C math, and so forth. So you still need to hash include these. And the place you do this is in what's called the global fragment of the module. What is the global fragment? It looks like this. So up to what we've covered so far is that we start the definition of a module by saying export module and then the module name. The global fragment has to come before this statement. So it's in this space that you see here. And the way it's defined is by just putting module semicolon, and then any hash includes that you have need to go in this space here. Also, one thing to note about this is if you do hash include anything in the global fragment, it will leak to other translation units just like they would prior to C++20. On the other hand, if you're just working with modules or the header units that are the analogs of the standard library headers, you can prevent leakage. And the flip side of this is that you have to explicitly state that you want that module to be imported elsewhere. So for example, if we define a module A that imports a module B, we would start out again by defining it and then putting the statement import B. So this, like hash including something, this is going to import module B into module A. And so you'd be able to use anything in module B inside this module A. Then if you import module A into another module C, module B will not be implicitly imported. If you want it available, then you have to explicitly put an import statement as well here. So there are two ways of looking at this. One is without this, then the module B will not leak into C. But if you do want it, you can get it, but you just have to explicitly state that you are importing it as well into the same module C. There might be cases, though, where you have a situation like this and you want module B to come along for the ride. So in that case, you use the export import statement. So again, this is a case where we might want module B to be exported along with module A. And so what you do is just like before, we define module A, and then we're importing module B like before, but if we put export before import, then what this will do is this will also be imported anywhere the module A is imported. So then it's no longer necessary to explicitly import module B into module C like we had to do before. So all this talk about export import, of course, reminds me of George Costanza. And so that brings us to next topic, mathematical concepts. So just a little nod to Art Vandelay, the import-export business. Okay, so mathematical constants. These are convenient const-expr mathematical constants which have been defined and are there available for use. And these include some of the most commonly used in math and statistics. For example, the constant e, pi, 1 over pi, 1 over square root of pi, and square root of 2. And of course, the nice thing here is, okay, they're const expr, but they're just doubles. So yes, you get better efficiency, but that's really not as significant as the fact that they are defined in one place. And so you can avoid cases where one developer defines E out to say 8 decimal places and another one out to 12. This way, it's a consistent definition across the board wherever it's used. To use these, you need to import or hash include numbers. And instead of just being scoped with stud, these are scoped with the stud numbers namespace. Just as an example, suppose we want to implement the function that you see here, then we could write it as follows. So you can see here I'm using inverse square root of pi, and then I'm dividing by square root of 2 to get this constant in front. I'm sorry, I was going to fix this. I will before I give them to Lloyd, these slides to Lloyd to post, but this should be in green as well here. But you can see for sine pi of x, we just use stud numbers pi, and then here we're multiplying y by 1 over pi, so we multiply by stud numbers inverse pi. Now, one thing that I found a bit curious is there's no constant for 1 over square root of 2 or square root of 2 pi. And these are used all the time, especially in statistical calculations. However, they do define one for 1 over square root of 3, which I've never seen used, I mean, in standard mathematical formulae. So despite the first two being far more commonly present in standard math and statistical calculations, they don't exist, but they give you one for 1 over square root of 3. So it's a mystery to me why they've chosen this. And that's why I had to actually calculate 1 over square root, or do the calculation for 1 over square root of 2 pi, as you saw in the previous example. In the Boost Math Toolkit, the constant set there does include both. So maybe in C++ 23, they'll bring them in. So it would be nice if they did. Okay, next up, the spaceship operator. All right, so to demonstrate this, I'm going to use an example here with a complex number class, which I'm going to call my complex. And just for review, so two complex numbers are of the form x plus iy. where I is defined as the square root of -1, and the x and y terms are real numbers. And then equality is defined when the real and imaginary parts match up exactly. So x1 is equal to x2 and y1 is equal to y2. We can also define inequalities by using the norm of the complex numbers. So what that means is it's just the square root of the squares of the real and imaginary parts, as you see here. So we will define Z1 to be greater than Z2 when the norm of Z1 is greater than Z2, and the norm is defined as you see here. And then likewise, going the other way, we get the inequality in the other direction. But the cool thing is that, well, logically, if we define equality and less than, then everything else follows. And that's what the spaceship operator does for us. This way, we don't have to define all 6 comparison operators anymore. Once we've established equality and less than, everything else follows. Okay, so in order to use the spaceship operator, it's actually in the standard library, you have to import the compare header unit. Excuse me. The other thing is unlike the standard comparison operators, the return type is no longer Boolean, and instead there are 3 categories of return types. First is strong ordering, and what this means is that any 2 values can be compared. So for example, integral types, you can always compare less than, greater than, or equal for integral types. For floating point types, for example, real number representation, as we're doing here with double precision, you might have an infinity representation or an NaN representation. So these are not comparable. So this is, in this case, we would use the weak ordering category. There's also a partial ordering category, and without getting into details, there are some weird cases where you could have all 3 of these being false simultaneously. If you want more information on this, you can find it on good old cppreference.com. But for our case, we will use stood weak ordering because the real and imaginary parts are represented by double precision types. And for each of these categories, there are then 3 possible outcomes: less, equivalent, or greater. Now, to set this up, the first thing you need to do is implement the equality operator, just like you would prior to C++20. Then the next step is to implement the spaceship operator itself. And inside, you are going to use the definition of less than and equality, which is defined first. Less than is defined inside the implementation of the spaceship operator. And in our case, again, the return type is going to be stood weak ordering. Okay, so the first thing we do is implement the equality operator. And so it's the usual thing. So it's an operator on the myComplex class. It's going to be a Boolean return. It's going to take in an external myComplex object. Just call it RHS for right-hand side, and of course it's const. Now for the real and imaginary types to be equal, since we're using floating point types, we're not going to check for exact equality. Instead, we'll just we'll use a tolerance. And so if the difference is, the absolute value of the difference is within some tolerance, then we will take them to be equal. So real and imaginary will be equal if the absolute values of their differences are within this tolerance. I've just used the default that they use in Boost. So if these hold, then we treat Z1 and Z2 as being equal. If not, they're false. So again, this is just like you would do prior to C++20. The next step, though, is to implement the spaceship operators you see here. So it's the same form. It's a member operator on the class. We're going to take in an external right-hand side object and run through the comparisons here. The first thing is you define less than. And what is our less than condition? It's if the norm of this is less than norm of right-hand side. And to do this, just using the stood hypot function. And if this holds, then instead of returning some Boolean type, we return this weak ordering less return. Next, we're going to use the definition of equality that we've established here. And so if this is true, then we will return the equivalent case. And then if neither of these hold, then it's greater than. You might be wondering here, well, we've already defined equality out here. Why do we have to use it in here? This last point might seem redundant. Well, the fact is this is just the way it's specified in the standard. And if you omit one or the other, either equality or the equivalent case inside the spaceship operator, then you can get results that are different than those that were originally intended. So again, it might seem a little weird, but, and when I first looked at this, I wondered, why do I have to do this? But it's just the way it is. Also, there is a default spaceship operator. My word of advice here is to use this with caution. There are some things that might be obvious. I'm not going to go into what it is here, mostly for the types of things that we're concerned with in my area is computational finance. If we had to do this, then we would more than likely be implementing the spaceship operator rather than relying on defaults. Okay, next up are ranges and views. And so this is a view of the range. Okay, so what do ranges do for us? Well, they provide abstractions of STL algorithms that are more intuitive, as we will see here momentarily. More specifically, what this does for us is it lets us avoid using the begin and end functions that we need to use in the regular STL algorithms. And then what views do is they allow certain operations to be performed. And when I say an operation here, it's something similar to what you might find in an STL algorithm, but hold that thought for the moment. We'll come back to that. But essentially what you're doing is you're allowing some operation being performed on an STL container without actually modifying the container. So if you're familiar with working with views in databases, it's a similar concept. With a view in a database, you can see the results of a query, but without actually the view gets stored and you can see the results, but you are not physically taking the results and putting them into another table, nor are you actually modifying the original data. The other thing that they do for us is they support functional behavior, which is kind of cool in that we can take multiple views and then pipe them like we would in Linux scripting. Okay, so to start off, we'll look at some examples of ranges. And first we'll compare them with the count-if STL algorithm. So it's the usual example. We're going to define a predicate to determine whether an integer is odd or not. And so we'll just take a vector of 1 through 9. Then to find the number of odd elements, we use the usual count-if algorithm. And as usual, we have to say from begin to end and then apply the predicate as you see here. If we do the same thing with ranges, though, it's a bit more intuitive. All we need to do is take in the container and then put the predicate, and we're done. So we don't have to mess with begin and end. So we've got one fewer term, and all it is just the container itself. So to compare, you can compare this with this, and this is more elegant. Incidentally, because I can't see the Teams interface, if you do have a question, maybe Lloyd or somebody can let me know. But I can't see it. You can also there's also a views version of transform, and so in this case, let's define an auxiliary function that will just square it'll take the square of an element, as you see here. And again, we'll start off with just using a vector 1 through 9 of integers. The old way, if you want to take the square of each and then place it back in the same vector, you'd say v dot begin, v dot end, and then v dot begin again to place the result starting at the beginning of the same container, and then you apply the auxiliary function as you see here. We can do the same thing with the ranges version as you see here. So in this case, instead of v dot begin, v dot end, again, we just put in the container itself, and then v dot begin, which says start placing the results at the beginning of the same container. And what that result will be the square of each element. So again, it's a bit cleaner. So you can compare the two. So this is, again, a bit more elegant than what you see up here. Just a few remarks. In the previous example with the ranges view of transform, we took the results and put them in the same vector, but you can also use back inserter with ranges. And so if we take the same example, the same vector v, but now suppose we want to put the results in a different vector w, we just take the source and then back insert or target, and then the auxiliary function here. I'm sorry, I'll need to correct this, that it should be with the integer template argument. But the idea is the same. All we need is the target, I'm sorry, the source, the target, and we're done. So no dot begin, no dot end. It's just very easy. Boom, boom, boom. On the flip side, there are not any range equivalents yet for numeric algorithms or parallel algorithms. I don't know what the status is on these, if these are planned for C++ 23 or not, but they are not available yet in C++ 20. So moving on to views, the good news is views are really, really cool. And again, for the reasons I mentioned before, is that you can perform operations on an STL container without modifying it. So it's also very efficient. This is all done in a lazy way. I'm not an expert on the details, but just suffice it to say that you can also reap some efficiencies from this. And also part of the efficiency is you don't have to take the results and copy them to another container. Everything is done in situ. And then also there are the functional capabilities that I mentioned before, and we'll see an example of that coming up. So some examples of the views that are available. One is called take. And what this will do is it will take the first n elements of a view or of a container and metaphorically discards the rest. So what it's actually doing is it's ignoring the rest because it doesn't delete anything. Another one is filter, and what this will do is filter in a set of elements according to some predicate. The one view that's very useful that has an equivalent in the set of STL algorithms is transform. And again, it's the same idea. You can modify elements of a view, but they are not modified in the original data does not get modified. And then finally, there's a view called drop that will remove, again, metaphorically, the first n elements of a view or a container. But again, what it's really doing is it is ignoring those elements. Now, the bad news is that the choices are still somewhat limited. There are more views than these, but those that might really be useful to those of us who do quantitative programming are the equivalents of algorithms such as countif, findif, partial sum, adjacent difference, and others. The view equivalents of these do not exist yet. They might be included in C++ 23. There is what looks to be a draft or a draft version of some of these, and they're located on Eric Niebler's GitHub site. It's the library name is ranges v3. That's v-3. And if you want to take a look at those, you can. But right now, they're not available. All right, so to look at some examples of views, first we're going to just proceed naively. And for this, we'll take a vector of double precision values, and we'll just generate them using the IOTA algorithm, as you see here. So this will generate the 10 elements from minus 5.5 up to 3.5. Okay, the first thing we'll do is we'll apply the take view. And so what this is going to do is it's going to take the first 5 elements. And so if we assign this to the view called take 5, we can just print these out using a range-based for loop. You can use a view inside a range-based for loop. And this is what you'll get. So you see, we're just taking the first 5, 1, 2, 3, 4, 5. One thing to note here is the return type of this thing here. If you were to actually inspect what it is, it's going to be some ghastly template type. And the other thing is, as I understand it, is it's implementation specific. So you'll have a different type for different compilers, and it's going to be some long, really ghastly template type. Fortunately, because of auto, we don't have to worry about it anymore. So auto is really earning its pay here. Okay, next we'll apply the filter view. And so we're going to take this result here, take 5. And so instead of a container, now we can just put a view inside here. So it will accept either one. And what it's going to filter through are the elements that are strictly less than -2. And so that's going to leave us with these 4 elements that you see here. Next one is we'll apply the transform view. And so this is going to take everything in 2 below and square it. And then finally, what we'll do is we'll apply the drop view, and we'll drop the first 2 elements, and that will leave us with these 2. But again, these are handled by the views. They're not stored anywhere, and the original data is not modified. Then finally, we can take the results and we can use them inside an STL algorithm. In this case, the accumulate algorithm. So, it's trivial, but we'll just add the elements that remain. And so we just use the accumulate algorithm that you see here. Okay, now this example might not be too terribly exciting, but this is going to change momentarily. But first, as I hinted at before, as we saw, we can use views inside STL algorithms themselves. And so we looked at the example of using std accumulate. We could also use them inside the transform algorithm or the ranges version of that algorithm. We could also find the maximum element in a view. So I've qualified this with most. There may be some that for which this won't work, but everything I tried seems to work. And I can't give you a source of, the exact information on if there are any algorithms in which you cannot use views, but for all intents and purposes, it almost surely it will work. As far as taking the results of a view and making copies of them and storing them in an STL container, there's no function yet that will do this. There was a function that was proposed. It's called to. And so to copy from a view to an STL container. My understanding is this has been postponed until C++ 23, but for now you can just use a range-based for loop to do this. There is a version of it, again, in the ranges v3 library, which again is under, you can find on Eric Niebler's GitHub site. Okay, now something really cool. And this is the functional approach to using views. So we'll start with the same vector W. And ultimately, we're going to get the same drop to view. So we're just going to start by assigning it first to the take 5 view like we had before. So we take in the vector W, and then it's going to take the first 5 elements. But then we can take this result and then we can pipe it in to the next view that you see here. So instead of taking this result and then explicitly putting it in the argument, instead we can take that out and just pipe this result into the next view, which is the filter view, as you can see here. And then all we do is we just put in the auxiliary function. Same thing, we can take this result and then pipe it into transform, and then this result and pipe it into the drop view. The result will be the same as we had before, those last two real numbers, and then we can pop the result in again into the accumulate STL algorithm, and we get the same result. So again, it's not the most exciting example, but this is pretty cool. And if they expand the selection of views to more analogs of existing STL algorithms, it's going to be even cooler. So the upshot here is, obviously, this is more elegant than what you saw before. And so I guess the moral of the story, though, is to stay tuned, because coming up probably in C++ 23, this is going to be expanded and will be a lot more useful. Okay, finally, I'm going to talk about the dates addition to C++ 20. And speaking of dates, that is Rodney Dangerfield trying to find a date on the celebrity version of the dating game in 1990. So little trivia, this is former NBA coach Pat Riley. He was also on the show. This is some soap opera actor. Yeah.
Just to jump in real quick, I'm seeing Robert's hand up. So
okay.
A question.
Yeah, yes. Can you hear me?
Yeah.
Yes.
Oh, so on all your examples where you show STD accumulate, you would say drop to begin, comma, drop to end. Can't you just say drop to using the new feature that you previously presented?
That's yeah, that's what I did here.
Well, yeah, but the last line there, it says STD accumulate, drop to begin, drop to end, and 0. Yeah. Can't you just say drop to?
No, because there's there are no range versions of the numeric STL algorithms.
Oh, okay.
So that's why you need to use these.
Okay.
Okay. Yeah, I would like that too, but you know, it's the way it is at present.
And I did have another question.
Oh, sure. Go ahead.
But it's about the spaceship. We could do that later, or I could ask it now.
Shall we hold that in abeyance? Because the dates part is the last part, and then
okay.
Is that okay?
Sure.
Okay. Cool. All right. All right. So back to dates. It's on YouTube, so I won't spoil the result if you want to see what happened. All right, so C++ 20 finally has some date-related classes, which is very nice because these are particularly useful. Again, I don't want to sound selfish, but for my area, which is computational finance, and you're going to find dates being necessary for a lot of bond and fixed income calculations. And this includes things like fixed income derivatives, which can become pretty mathematically intense. So it's not, we're not just talking simple bond calculations. So these are really, really useful for these purposes. Now the deal is this was expected in C++ 20. As far as I know, it still is, but so far I've not been able to find it included in Chrono for either Visual Studio or Clang. I haven't checked Visual Studio 2022, but I am using the most recent version of 2019, and there's an option where you can get the most up-to-date C++20 compiler, and so far I'm not able to import Chrono and get dates. So the workaround that I'm using here is I've downloaded the source code from Howard Hinnant's GitHub site. So he's the author of the date library. Just a few notes about this. It's very nice to have these, but the thing to be aware of is that some of the common operations that you have to use, again, I think of, my own field, which is finance. In order to do some of these common operations, they actually involve multiple steps in casting. So it's a little bit convoluted. So it's something to be aware of. Also, I'm not able to find much in documentation. So if you want to find out how to do something, you'll probably have better luck looking it up on Stack Overflow. And in fact, some of the things that I looked up, it was actually Howard Hinnant himself who answered the questions. And also, just a side note, some students of mine and I have been working over the last year or so. I mean, it's something that, we pick up, put down, pick up, put down, but we're close to having something that it's a C++ library that mimics Excel dates and date functions. And so what we've done is we've wrapped this date library inside another class. And so these steps and casting that you see here are all taken care of behind the scenes. And then also it's with the familiarity of Excel, which unfortunately is still ubiquitous in the field of finance. It's like the thing that wouldn't die, but again, it's a reality. And so that was the motivation behind it. So anyway, some examples now of using the date library follow. So first of all, how do you construct a date object? Okay, first of all, if you use the source from GitHub, then you'll need to hash include it. There are actually there are more than several ways that you can instantiate a date object. There are different formats you can use. I'm going to use year, month, day because it's obvious. You have year, month, and day. There's the American format, which is month, day, year. There's the British format, which is day, month, year. And then the format that's used in Japan, but is also very common throughout international finance, is to put year, month, day, because that way it's obvious what it is. So that's what I'm going to use here. And so there's a class called year, month, day, and the way you create an instance of it is you give it the year, but it has to be in terms of a year object. So that's why you have to put date, year, and then the actual year in the argument here. Same for month and same for day. Conveniently, the stream operator is overloaded for all of these date types. An alternative is to write the year as with the suffix of Y for year. You just spell out the month, no quotes, and then the day with a D suffix. Excuse me. There are other class formats possible. Again, you can month, day, year, or day, month, year. Okay, a very common thing that you have to do in fixed income finance is to calculate day count conventions, because different bonds will have different day count conventions. And if you don't get them right, then if you're on a trading desk and you use the wrong day count convention and other desks get a whiff of that, then they can arbitrage against you. So day counts are very, very important in finance. So to do this, the way it works is they're based off of integer values using the default epoch in the date library, and that is the Unix epoch of 1st of January 1970. And so what this will do is it facilitates the number of days between two dates. Excel, for example, uses the epoch 1st of January 1900, but the default in the date library is the Unix epoch. There are others that you can choose. I think that there's a Julian calendar and a Gregorian calendar, but we'll just use the default. It's easy. And for most modern day finance, you don't need anything before that unless you are dealing with, say, pension calculations or so forth, then you need to go before 1970 because of birth dates of the participants. So anyway, what we need first is the ability to calculate the number of days between two dates. But here's where you get into this casting and conversion issue. Is in order to do this, if you have a date object like we just saw, you have to convert it to what's called a sysdays object. And because there's a member function called count, and then that is what allows you to determine the number of days. Technically speaking, sysdays is what's called a time point in the chrono library. It's also now aliased with date. And what it does is it represents the same date as your, say, year, month, day object, but it's converted to a sysdays object. Again, there's a lot going on behind the scenes. I don't know a lot about it, but the upshot is, for us as users, this is what you need to do. So one thing you can do is you can find the number of days since the epoch. So 50 years hence would have been 1st of January 2020, so right before everything went to hell. And the way you do this is you convert to a sysdays type, and then there's a member function called time since epoch, but then to get the number of days, you have to call the count function. But what we're really after is to be able to count the number of days between two dates. And so in this case, if we have two date objects, YMD and YMD2, we have to convert each to a sysdays object, and then we take the difference between the two, but in order to get the number of days, we have to call this count member function. Once you get the number of days, then, for example, in the trivial day count conventions like actual over 360 and actual over 365, you just divide by each, and then this gives you the day count adjusted year fraction. So for 365, it's going to be exact because there are no leap years involved here, but for 360, it's going to be a little bit greater. But something a little bit more useful, because there are other day counts that are a bit more involved and which are used a lot in fixed income trading. One example is the 30 over 360 day count. And what this does is it assumes there are 30 days in each month and 360 days per year. And again, this one is very, very commonly used. So to show this, I'm going to define a function called 3360, and we're going to take in two year, month, day objects, as you see here. Oh, I was going to just one thing I want to back up here. I forgot to mention. this count function, it will return an int type. So you go through all this conversion and everything, but ultimately what it returns is an int. Now back to this example. Where it gets weird though is in the previous example, count returned int. But here we need to get the value of the day. So for example, if this is November 30th of 2021, we might want to get the number 30. In order to get that, we need to take the day member on this date and then convert it to an integer value. But in this case, we have to cast it to unsigned, which makes more sense. But still, what's strange is when I try to cast it to an int, I get a compiler error, but casting it to unsigned is no problem. So again, if you're doing anything like this, is at least as it stands now, this is what you need to do. So now we have the actual integer day values for each of these dates. And we will need these because this day count calculation requires them. As you will see here, this just adjusts everything to 30 days per month. And then to get the day count adjusted number of days between these two dates is calculated as you see here. And this is why we need the actual day values, is because the calculation requires them here. And then to get the day count adjusted year fraction, then we just divide by 360. Another thing to note here is these are the year object members on these date objects here. And it turns out that in order to get the number of years between the two, we do not have to cast these to sys dates. So again, in some cases you have to, some cases you don't. It's just something that you might need to be aware of if you're working with these. Okay, there's some other common operations, and I'm using finance because this is where you need to do odd date calculations. One is to check if a date is on a weekend, because if, say, you're expecting a payment on a certain date, but it falls on a weekend, then you have to adjust either, say, the Friday before or the Monday following. Sometimes you need to check if a date is a leap year. And then there are cases where you need to add days, months, and years to a date, say, to construct what's called a term structure of interest rates, because you're taking market interest rate data and then you are interpolating and estimating forward rates, say that might be 2 days forward, 3 months, 6 months forward, 2 years, 5 years, 10 years, 30 years forward, this sort of thing. So you need to be able to add days, months, and years to the current value date, which is the date that you're getting the market data from. Okay, so to check if a date is a weekend, it would be nice if there were, say, an is weekend member function on the date class and just returns true or false, but there isn't. What you need to do is, again, convert to a sysdays object and then construct an object of the weekday class. What this means, it doesn't mean weekday as in Monday through Friday. What it means is, what day of the week is it? So this could be Sunday through Saturday. And so what you do is you construct this weekday object with the sysdays object that you convert to, and then you can, this day of the week object, then you can check If it's a Saturday or a Sunday, then it's true, it is a weekend. If not, it's false. And then we can just call this lambda and get the result. So this is a weekday and this is a weekend. Okay, for adding days, months, and years, again, it would be nice if there were functions, say like add days, and then you just put whatever the integer value is, or add months, add years. Again, as it stands right now, these don't exist. So again, you need to convert to sys days again, and then you can't just add an integer value, you have to add a days object, a month's object, or a year's object. And so, for example, if we take our date object YMD1, convert it to sys days, and then we add 3 days by adding a days object constructed with 3 days. Same for months and same for years. I'm not sure why this is the case. There might be a reason, but it's, again, there are more steps that you need to go through to just add days, months, and years. Then checking the results. First of all, these 3 return types, they're all different types. So again, it would be nice if they were just all consistently some consistent date type, but they're not. Again, it's just if you're working with this, it's something you'll need to be aware of. Another thing that I found is that this is incorrect. So we're starting with November 14th here, add a year to it, this should be November 14th, 10 years later. So I'm not sure what's going on here. Maybe it's been reported, maybe it'll be fixed by the time it does go into the major compilers. But if you're using it now, something to watch out for. However, there's another way you can do this, which is a little bit simpler, and that's to use addition assignment, which is defined for the date class. So this is the year, month, day, date class. And so in this case, you can just add years, as you see here, and it will update this date to be 19 years later, and the result is correct. The other thing that's convenient is you still have the same object type here. So the upshot here seems to be if you need to add days, months, or years, use addition assignment where you can. This is what we've used on our Excel date class, and all the tests pass. Let's see. One other thing just to be aware of, this is not necessarily an error or a problem, but it's just something to be aware of. In financial calculations, if you add a month or a number of months to a date that is already an end of month, then you expect the result to also be the end of the month. So for example, if you add a month to April 30th, in the financial sense, you expect it to be May 31st. But the way that these calculations work, it's not adjusted. So if you do need that, you would need to adjust it yourself. However, as far as I can tell, there is no function to check whether a date is end of the month or not in the date library. There is a thing called a year, month, day, last class, but what it does is it represents the last day of a month, but you can't take an arbitrary date and check whether, you can't use it to check whether a date is the last day of the month. It'd be nice if something like this did exist. So anyway, just a little bit, I don't mean this to be a shameless plug, but it's just an example of how you might take what we now have and then wrap it into something that is more useful for the domain you're working in. And in our case, what we're doing is we're essentially mimicking Excel dates. So we're almost done with it. Again, it wraps the C++ date, the C++20 date library where we can. And we use addition assignment for adding days, months, and years because that seems to work. We have an end of the month check, but what we do is we just take all the possible days in a month. So 28, 29, 30, 31, and it's hard coded, but it works. And also our adding months will preserve end of the month. And we use the January 1st, 1900 epoch, like in Excel, rather than the Unix epoch. So I'm hopefully get this wrapped up soon, so maybe people can start using it. Just to show you the function and constructor declarations. There's a default constructor. You can construct a date from the Excel serial date. So this is the integer representation in Excel, or you can construct it with just an integer type. So just unsigned year, month, and day. So again, all that year, month, day stuff is taken care of behind the scenes, and the user doesn't have to worry about it. We can add years, months, and days, again, just by taking in the integer types. Maybe we should make that unsigned, but you get the idea. There are accessors where you can get the days in a month or the day of the week. We can determine whether a month is the end of the month, whether the year is a leap year, or whether the date falls on a weekday. And then other accessors that you see here, and mutators. If you change one of these, then it will update the serial date and vice versa. And then the typical operators. So you can get the number of days between two dates, addition and subtraction assignment increments, and then the comparative operators. As you may notice here, this hasn't been updated yet for the Spaceship Operator, so that's on the list. So we need to get that done. So anyway, that's all. Thanks for tuning in, and hope you found this useful. So I can, there were some questions, so I'm happy to take them now.
Yeah, Robert, you still had one, as I remember, so go for it.
Oh, okay. So I'm a little bit confused about the Spaceship Operator, and I'm thinking of an example. He was comparing two complex numbers, but let's say you had 2 plus 3i and 3 plus 2i. They're not, one isn't less than the other, one isn't greater than the other, because the magnitudes are the same, but they're not equivalent either. So
that's right. That's yeah. I just used that as an example. That's why I used the modulus. So the inequality holds in the sense of the triangle inequality. That's what it was just a, to show as an example.
Yeah. So what do you get from the Spaceship Operators?
Well, you don't have to. You don't have to define all 6 comparator operators.
Okay.
So
well,
it's
what
just
are
oh, go ahead.
So what are the 6?
Equivalent, so equals. Not equal, so bang equals. Strictly less than, strictly greater than, less than or equals, and greater than or equals.
Okay.
Kind of like what you saw on that second to last slide for our date class, and then if you remember, but let's see, trying to see where, not sure where the share went. Let's see.
What are you looking for? Share the screen?
Oh, I'm still sharing. Oh,
Yeah, you're still
I
sharing.
just,
Just pop up the.
yeah, okay. So I can yeah, I can just bring that up here. So like you see here, so for our date class, we'll be able to replace these with the spaceship operator. So all we will need is the equals or the equivalent operator, and then the spaceship operator, inside which the less than inequality will be defined. Does that answer your question?
Yeah, I'll be thinking about it, but I believe so.
Okay.
Okay. Bob, looks like your hand's up. Go for it.
Yeah, my hand is up. To add more to that comment, the ordering in complex is a partial ordering. It's the third of the three things that you have, because it is quite the example that somebody just gave, that it can be none of the three, less than, greater than, or equivalent. So that defines the third of the three options that you presented, which is partial ordering. And in fact, mathematically, the complex numbers are partially ordered. They're not ordered.
Yeah, I'm aware of that. Again, it was just so I could show an example.
Yeah, but the weak ordering is wrong, and there are actually errors in the code that you showed.
Okay, I'll take that under advisement. Feel free to email me. I can.
Okay.
I can. Not sure if I can give it here. But again,
Yeah.
I just needed an example was the main thing.
Yeah, it's always nice when examples are correct. Because when you had an implementation of the operator of the spaceship operator in terms of two of the others, then the third option ended up being wrong.
Okay.
Because.
Okay. Well, please.
Okay.
Please send me your
Okay.
comments, because I'd like to see them.
I have another example also.
Okay.
Another error to point out that you might want to fix. In the module example, your private functions were written such that they set the value of module variables, and then but their return type was void. And then when you use them in your public function, you had put auto in as the return type and that auto would end up being void. And yeah, that's
oh
it.
yeah, that's right.
That's
Yeah,
correct.
yeah,
Right there.
yeah. That's
You would
incorrect.
want to
Yeah,
use
thanks.
down in the
Yeah,
and the other one would
yeah.
be.
That what I should have. Yeah, in fact, this is what I should have done. And yeah, I think I did this first, and then I put these in later. What this should be is. Yeah, you're right. This should be that, and
No, but it was a really useful summary of
yeah, it's just
some good new stuff that's in C++20, and I appreciate it. I just think you probably want to fix those errors before you publish it.
oh yeah, sure, yeah, thanks. Yeah, so it should be. Yeah, thanks. Okay.
But then there is no return type. So the fx is set inside the function. So there is no return type from.
Yeah, I know. That's the.
There is no equality. There is no assignment. Just
Yeah. Well, that was
fx equals.
that was the point I wanted to make, but it was an error. What I wanted to point out here is that these are like they're like member functions on a class, so that they're internal to the module among all the functions. So we can, like a class, we can assign them here.
No, that's not correct.
Oh, I'm sorry.
That will not compile.
Oh no, that's right. No, this is completely wrong.
You want
Yeah,
want to call the functions with no return type, with no return.
Yeah, this is what I want. This is what I want here.
But you still have to call
them. Yeah.
The main concern is the return type of the function.
Subroutines.
Yeah, I need this is what I need. Yeah,
there you go.
I'll go back and look at the source code. It all ran in my sample code, and I might not have updated the slides. Okay. I think that's what happened. So
yeah,
this is what I want.
Right.
Oops.
And then.
Oops. Yeah. Thanks.
Bye. But then you don't need to type, no double.
Yeah.
That's it. That's correct now. Particularly.
Well, I think that there's no X or Y defined. I think it's the double F underscore X and F underscore Y.
X and Y are.
Oh, I see. It's passed in. It's passed in. Never mind.
Yeah.
Okay.
That's it.
Yeah.
That's correct.
Yeah, there we go.
That will compile, I think.
Yeah. Yeah, as I said, my source code compiled, and I probably changed it in there, but I didn't change it when I came back here. Okay, yeah, thanks.
You're welcome.
Okay, Jeff, you've got two hands up, so you got something really cool.
What? Sorry about that.
That's okay.
Yeah, I have a couple of things. First about modules. Sorry, I'm still catching up on 17, so I haven't read very much about any of this stuff. Are modules then implemented entirely in source files?
Yeah, that's one of the things that seems to still be getting worked out. So, for example, in Visual C++, the default way of doing it is if I want to add a module, I come here and I can say add a module. And when I do that, it's going to create an .ixx file.
Oh,
interesting.
Okay. Now, what I was able to, again, my understanding is that with other compilers, the default behavior is different. So I can't remember which is which, but in Clang or GCC, it's you implement it as a regular source file like .cpp, and in fact, you can do that I could define a module in Visual Studio and make it a CPP file. That would work. There's also something like an MCCP extension, something like that. I think that was with Clang. But this is some of this I think is still getting worked out. And then of course you can set your own configurations.
okay. Okay, so basically .h is literally gone.
Right, yeah, you don't need a
Okay.
Yeah, you don't need a header file. It's
Yeah. How does that affect what would normally be inline functions?
I'm not sure. I'm assuming you can still, you know, if you wanted to, you could, you know, do that if you wanted.
Okay.
Um,
Yeah, because I'm thinking the vector is all pretty much inline since it's all defined in the class. So,
yeah.
okay. Well, that's
Yeah.
yeah. The other question that I had involved the spaceship operator, and maybe I
Okay.
missed it, but we saw kind of how to implement it, but I'm not clear on how to actually use it in code. Maybe I missed that slide.
Okay. Well, the idea is that, let's see if I can find it here. Okay, so before C++20, you would have to, you'd find this one and
Right.
inequality or non-equality, you know,
Right.
and so
And
forth,
all
right?
the others.
Yeah, so you'd have 6 of these.
Uh-huh.
But the idea is all those go away, and that's what you have right there.
Right. And that's, from my understanding, that's the implementation. I mean, do you actually use the free character operator itself in user code?
Yes.
That's what I'm looking for. That's what I'm
Yeah. So
unclear on.
yeah. So let me see if I can find I don't know if I have the examples here. Let's see. I guess I don't have it in. Maybe I can put that in. I don't have anything in here. But yeah, that's the idea. So you can just use them as you did before, but when you define them, you don't have to define all 6.
Right. But is there a case where you say if Fred, spaceship operator Barney, is there a case where you actually do that in user code, or is it strictly a matter of it being a shortcut to defining the 6 and you just use the 6 in user code?
I'm not aware of any.
Okay. Okay.
Yeah.
Okay. So it's just basically a shortcut to defining
Yep.
those operators. You just continue to use those operators.
Mm-hmm.
Okay. Okay.
Yeah, that's my
what I
understanding.
was
That's how I've done it, and that's my understanding.
Okay. Thank you.
Sorry for
Sure.
interrupting, guys. For the brevity of the video reasons, I suggest to stop recording and you continue discussing outside of the recording. Is that okay?
Sure.
Yep, good by me. Go for it, Robin. Thanks.
Okay, I'll stop recording.
Okay.